Welcome to Lecture 7 of the Wireless Communication course at Chalmers University of Technology. My name is Henk Wijmeers. In this lecture we will cover part of Chapter 9 of the book Wireless Communication by Andrea Goldschmidt. We will talk about different adaptation strategies such as rate adaptation, power adaptation, as well as joint rate and power adaptation. The main mathematical tool we will use is Waterfilling. The learning outcomes for today is that you should be able to explain the goal of adaptive transmission, the benefits and drawbacks, solve rate and power adaptation problems, and also derive and implement water filling approaches. Last time we talked about diversity approaches, where we send the same signal over multiple diversity branches, each with a different channel. The optimal diversity combining method is called maximum ratio combining, shown here, which involves taking the input signal, multiplying with the complex conjugate of the channel, and summing. This leads to an output SNR, which is the sum of the input SNRs. When the channels are independent over the different diversity branches, we obtain both diversity and array gain. Array gain is a phenomenon where the average SNR increases with m for a fixed SNR per branch. This phenomenon is independent on the channel statistics. Diversity gain we see when the channels are independent over the different branches, and the channel becomes more like an additive wide Gaussian noise channel with more diversity branches. This is shown here on the right, where we show the average error probability as a function of the average SNR for a different number of diversity branches. For only one diversity branch, we have the Rayleigh fading channel, for which we have the traditional average error probability. With more and more diversity branches, where we normalize the power with respect to the diversity order, we see that the channel approaches an additive wide Gaussian noise channel. Of course, this comes at a cost in terms of either delay, larger frequency bands, or more receive antennas. Diversity was one of the ways in which we could overcome the limitations of the wireless channel. An alternative technique is adaptive transmission. The goal of adaptive transmission is to maintain a certain quality of service even in the presence of a time-varying channel. So one thing we could do, which is non-adaptive transmission, is to fix the transmit power and modulation for the worst possible channel. But this of course will be very conservative. So a better strategy is to vary the power and modulation format based on the channel. To do this, we need to of course have channel knowledge at the transmitter. This means that we need to assume that the channel varies slowly over time so that channel state information can be fed back from the receiver, which estimates the channel to the transmitter. The system model is shown in the bottom here. The transmitter sends symbols, xi, from some constellation over a channel, which includes fading and noise. The receiver observes yi and recovers the data, plus estimates the channel. This channel estimate is fed back to the transmitter. The transmitter can then do different things. Given the input bits Ri, the transmitter could adapt the modulation format. For instance, in the case the channel is poor with a low SNR, the transmitter could decide to use BPSK. On the other hand, if the channel is very good with very high SNR, the transmitter could use 64 QAM. Similarly, the transmitter could also adapt the power. In order to have a fixed receive power at the receiver, the transmitter could thus do power control. There are other ways that you can adapt to the channel conditions, such as changing the bandwidth or the coding rate. These are not discussed here in this lecture. In order to treat adaptive transmission in a mathematical framework, we will need to make several assumptions. We will assume a discrete time channel, where for every channel use, we send one symbol during one symbol slot, Ts. The bandwidth is approximately 1 over Ts. The channel is assumed to vary slowly over time so that channel state information can be fed back from the receiver to the transmitter. The channel is assumed to be stationary so that the statistics don't change over time, and ergodic so that the statistics can be deduced from a single sufficiently long realization. The gain gk is the amplitude of the channel squared at time k. The noise is standard Gaussian. We can then define the instantaneous SNR at time k for a fixed transmit power P bar. P bar is the average allowed transmit power. The instantaneous SNR is P bar times the SNR induced by the channel. The average SNR, average over all possible G, is gamma bar. It is P bar times G bar, where G bar is the average gain of the channel divided by the noise power. Since G is stationary and ergodic, the distribution of the SNR is independent of K. And we will denote this distribution by P of gamma. Let us now look at the case without adaptation. In this case, we have a fixed target bit error rate with a fixed transmit power and a fixed modulation format M. When we fix the modulation format, we know that the rate will be equal to log 2m over Ts, expressed in bits per second, or bandwidth times log 2m. The spectral efficiency is the rate over the bandwidth is log 2m bits per channel use. So while this seems good, we need to take into account that the transmission can be an outage. So there is only transmission when the channel is sufficiently good, so when the SNR is high enough, such that the modulation format can be transmitted with the target bit error rate, we actually have data transmission. Otherwise, the channel is in outage. So with the fixed modulation format and the fixed power, we have a certain outage probability. The probability that the SNR is too low to support the transmission. The outage probability is defined as a probability that the SNR is lower than a certain threshold, where the threshold depends on the modulation format and the target bit error rate. The outage probability is defined as follows: the probability from 0 to the threshold value of the density of the SNR. We can then define an average spectral efficiency, because the true spectral efficiency cannot always be realized, because the channel is sometimes in outage. The average spectral efficiency is 1 minus P out, so the probability that the channel is in a good condition, times the spectral efficiency shown above. We can then substitute the outage probability and find this expression. So this tells us the average spectral efficiency for a case without adaptation. This average spectral efficiency will depend on the modulation format, as well as the threshold value for the SNR, as well as the density of the SNRs. We will now consider 3 adaptive transmission techniques. In the first strategy, we will adapt the rate for a fixed transmit power. The main idea is that we will use a larger order constellation when the channel is better, while maintaining a fixed target bit error rate for that constellation. Our performance metrics in that case will be the average rate and the outage probability. In the second strategy, we will adapt the transmit power for a fixed rate. So we use a fixed constellation format, but use more power for worse channels and less power for better channels. So the average power is fixed, and the performance metrics are the achievable SNR as well as the outage probability. The third strategy is to adapt both transmit power and rate. It will then turn out that we will actually use more power and a larger constellation when the channel is better. So this is in contrast to strategy 2, where we will use less power for better channels. We will fix in strategy 3 the target bit error rate and the average power, and the performance metrics will be average rate and outage probability. Let's start with the first strategy, rate adaptation for a fixed transmit power. In rate adaptation, without power adaptation, we will have a fixed target bit error rate, let's say 10 to the minus 3, and a fixed transmit power. For this fixed transmit power, we have a certain distribution of the received SNR, P of gamma, with an average value of gamma bar. We also have a set of modulation formats, M1 through Mn. Each modulation format Mj has Mj points. So for instance, we could have 3 modulation formats, QPSK, 8PSK, and 16PSK, with respectively 4, 8, and 16 points. For each modulation format, there is a certain SNR threshold that achieves the target bit error rate. So this is now shown on the figure in the bottom, where on the x-axis we show the SNR in dB, the y-axis is bit error rate. We have a certain threshold value of 10 to the minus 3 in this case for the bit error rate. We also show the performance of different modulation formats. We see that when the signal-to-noise ratio is more than 10 dB, we can use QPSK. When the signal-to-noise ratio is less than 10 dB, we have no modulation format available. When the SNR is above 15 dB, we can switch to 8 PSK. So there's a range between 10 and 15 dB for which we can use QPSK, and for all those SNR values we meet or exceed the target bit error rate of 10 to the minus 3. When the SNR is more than 21 dB, we can switch to 16 PSK, and so forth. So we see that we have different SNR ranges for different constellation formats, and a certain SNR range below 10 dB for which we can transmit nothing. We then have two performance metrics. The first one is the average rate. The average rate R bar is defined as follows. It is the sum over all possible modulation formats times the number of bits that can be transmitted with a modulation format times the probability that the SNR falls within the range for which we would use that modulation format. So for instance, for QPSK, the range would be from 10 to 15 dB. We also have the outage probability, which is the probability that the SNR is too low to be sustained with any of the modulation formats. This happens in our case when the SNR falls below 10 dB. In general, the outage probability is defined through this expression. It is easy to show that the first strategy, the rate adaptation for a fixed transmit power, is always better than not adapting at all. A natural second strategy is to adapt the transmit power for a fixed rate. We consider the following scenario. We have a certain average transmit power, and we want to maintain a certain constant signal-to-noise ratio at the receiver for a specific fixed modulation format. So we want to make sure that the signal-to-noise ratio, and thus the bit error rate, is always constant. We will denote the received signal-to-noise ratio under power control as gamma PC, and this is equal to the amount of power control times the signal-to-noise ratio before power control divided by the average power. Recall that when we don't do any power control, then P gamma is equal to P bar, and then gamma PC will be equal to gamma. Our first strategy will be to do channel inversion. So we simply apply a power control equal to gamma times P bar, power control equal to sigma times P bar over gamma. If we substitute this expression in here, we see that gamma PC will be equal to sigma. Now, of course, we need to figure out what is a sigma that we can attain. We find the sigma by considering the average power constraint. The average power constraint is this one. And then after some simple math, we find that sigma is obtained through this relation. In other words, 1 over the constant SNR value sigma is equal to the expected value of 1 over the SNR. It turns out that this value is infinite for Rayleigh fading. In other words, the value that we can achieve is sigma equal to 0, so that means we cannot transmit anything. So strategy 1 is in principle not very useful for many channel models. Another strategy is the channel inversion with cutoff. So we apply the same power control as before, sigma times P bar over gamma, but only for gammas that are sufficiently high, so let's say larger than some threshold value, gamma 0. We can then figure out what is the value for sigma through the same expression, but taking the integral only from gamma 0 to plus infinity instead of 0 to infinity. And then of course we'll have a certain outage probability, because in case the SNR is less than gamma 0, we cannot transmit anything. In general, power adaptation without rate adaptation does not lead to very promising strategies. Finally, we will consider our third strategy to adapt both the transmit power and the rate. Before we do that, let's look at something called waterfilling, which is a general approach to solve a certain class of optimization problems. The class of optimization problems we consider is shown in the first bullet. We consider certain constants AL, BL, C, and P all non-negative, and we would like to solve the following optimization problem. We want to maximize with respect to x an objective function, which is the sum over L, AL times log 2 C plus XL BL. So XL are the optimization variables. We will add certain constraints. So a first constraint involves the sum of the AL XLs, and a second constraint is that the XLs are non-negative. To solve this kind of problems, we will formulate a partial Lagrangian, L of x and lambda. We will work with a minus sign because it is easier to look at minimization. So maximization of the objective is the same as minimizing the negative objective. So the Lagrangian is the objective function plus the Lagrange multiplier times the constraint. In addition, we retain the non-negativity constraint separately. We can then look at stationary points of this Lagrangian by taking partial derivatives with respect to xl. So the partial derivative is easily found to be the following expression. And this partial derivative should be 0 in order to have a stationary point of the Lagrangian. We can then solve for xl, and we find the following expression, plus the condition that xl should be non-negative. Overall, we find that xl should be the maximum of 0 or a constant minus c over bl. And the constant should be such that the other constraint is valid. This solution is called the water-filling solution to the original optimization problem. Later we will see why it is called water-filling. It is important to note that when we replace all the sums by integrals, that the solution still holds. We will now apply water-filling to the problem of power and rate allocation. We will first consider statistical water-filling with discrete SNR values. We will assume to have a fixed target bit error rate and a fixed average power, and we aim to maximize the expected rate. We will focus on m-QAM constellations for which it is possible to express the rate as a function of the power allocation. For m-QAM, the bit error rate can be upper bounded with an exponential, which involves the SNR, the power allocation for that SNR, the average power, and the size of the constellation. From this inequality, we can approximate this by an equality and recover m. So this is the value of m for a certain SNR that achieves a certain target bit error rate PB. So m is written as 1 plus a constant which depends on the target bit error rate and a function of the SNR and the power allocation. In principle, here m can be continuous, which is the assumption that we'll keep for this slide. Now, in order to maximize the rate for continuous m and discrete SNR values, we will solve the following optimization problem. We will maximize with respect to the power allocation the expected rate. The expected rate involves an expectation over all possible SNR values with their probability times the rate corresponding to that SNR value. So when we have a certain SNR value, our rate will be log 2 of m, because that's how many symbols we can transmit. Then we can substitute back what is m, and we find this expression. So this is our rate. We have certain constraints. First of all, we have an average power constraint. So this is written here. The expectation of the power allocation is equal to the average power. And we have non-negativity of the powers. This optimization problem is exactly of the form as we've seen in the previous slide. So the solution must be of the same form. The solution turns out to be the following. The allocated power for a certain SNR is either 0 when the SNR is too low, or non-zero when the SNR is above a threshold value, and in that case the SNR is given by this expression. So the power here will be a constant minus 1 over the SNR. If we now substitute back this solution of P of gamma in the expression for m, we find that m has to be of the following form. So the size of the constellation as a function of the SNR is proportional to the SNR over a cutoff value gamma k for sufficiently high SNRs and 0 otherwise. So it follows naturally from the solution of the optimization problem that for low SNRs we don't transmit anything, and for higher SNRs we will transmit with more power and a higher order constellation. We can apply the same approach to the continuous SNR case. So the problem setup is the same as before, but the optimization problem is slightly different. We want to maximize with respect to the power allocation the expected rate. So for each power we have a certain PDF and we have the number of bits that are transmitted when we use that power. We can substitute m of gamma in this expression here. In addition, we have a constraint, which is the average power constraint. So the expectation of the power with respect to the SNR should be equal to the average power. Of course, the power should be non-negative. The solution is exactly the same as before. The power depends on whether or not the SNR exceeds the threshold. If the SNR is too low, we don't send any power. If the SNR is sufficiently high, we send some power. The amount of power depends on the expression here. And the cutoff value gamma k is fixed in order to meet the average power constraint. Again, we find the size of the constellation by substituting back the power in the size of the constellation expression on top. Let us try to get some intuition in the water filling solution. So here again is the solution of the optimization problem. The power is either 0 or some value depending on whether the SNR is above or below the cutoff value. Let's visualize this expression. Here I will plot on the x-axis the SNR, so gamma, with worse channels on the left side and better channels on the right side. Then I plot part of the power allocation p bar over k times 1 over gamma. So this is this curve here. I have a certain cutoff value, gamma k. So when the SNR is below gamma k, I don't send any power. When it is above gamma k, I will send some power. When I compute this intersection point here, then on the y-axis I find p bar over k times gamma k. So I just substitute gamma k in the expression here. And then I can fill up this region with water. For any SNR value, here's for instance here, the amount of power I'll allocate is equal to the water level. When I have an SNR value that is very small, I will allocate only a little bit of power, there's only a small water level, with a small order constellation. When I have much higher SNR, I can allocate more power with a higher order constellation. The value of gamma k, by shifting this to the left or to the right, will affect a number of things. By shifting gamma k to the left, the intersection point will shift to the left, so then the water level will also go up. That means the average power will be higher. When I shift gamma to the right, the intersection point will move to the right and the water level will be lower. So you can see by moving gamma k to the left or the right, I can make sure to meet my average power constraint. So far, we found the following solution. We found that the size of the constellation as a function of the SNR has this expression depending on the power allocation, where the optimal power allocation is given by the water filling solution. We can also find that the size of the constellation is equal to the SNR divided by the cutoff value of the SNR. In all of these cases, m can be any real number. In practice, m will come from some discrete set, for instance 2, 4, and 8 points. What we can then do is the following. Let's choose a water level, gamma k star. Given the expression here on top, we can then note that there are certain fading regions, so certain values for gamma, for which we will use certain constellations. So when gamma over gamma k star is between 2 and 4, we will use the constellation with 2 points. When gamma over gamma k star is less than 2, we will use no constellation at all. When gamma over k star is more than 8, we use 8 points. We can then do a power adaptation for each region. So this power adaptation will look as follows. We can then compute the rate associated with this value of gamma k star. So then we can, in principle, optimize with respect to gamma k star to find the best possible value that leads to the maximum expected rate subject to the power constraint. The performance of this approach is visualized in the figure below. We show as a function of the average SNR in dB the spectral efficiency. There are a number of curves in this figure. We show in red the curve obtained with a continuous modulation format, so basically the standard water filling approach. And in blue, the results obtained from the procedure shown in this slide for 5 different modulation regions. When we reduce the number of possible constellations, of course, the spectral efficiency will drop. All of these results correspond to a bit error rate of 10 to the minus 3. In addition to statistical water filling, there is also deterministic water filling, also called adaptive loading. In deterministic water filling, we have the transmission over n parallel channels with a total power constraint P. Each channel has a certain fading envelope, alpha I, plus a bandwidth and a noise power spectral density. We aim to find a power per channel and a modulation format per channel to maximize the total rate. The optimization problem now becomes as follows. We maximize with respect to P the sum rate over all of the channels. So we take a sum over all the channels and compute the rate per channel. This is log 2 of 1 plus the SNR over that channel. We have a total power constraint and all the powers are non-negative. You can see that in this optimization problem and in the problem formulation there is nothing statistical anymore. That's why we call this deterministic water filling. The solution is again of the standard form, where the allocated power is equal to the maximum of 0 and 1 over a cutoff value minus 1 over the SNR, normalized with respect to the total power. The cutoff value is chosen to maximize the total power constraint. In combination with mQuam, we can then of course find a value of m corresponding to that transmit power to achieve a certain bit error rate. Deterministic water filling also has a nice interpretation. In this figure, we show on the x-axis the channel index, on the y-axis 1 over the SNR per channel. We have a certain water level again, 1 over gamma c, which we can raise up or down. The power we allocate to a certain channel depends on the water level. The water level is given by 1 over gamma c, and the floor value here is 1 over the SNR of that channel. This means that channel with a very high SNR, so with a very low 1 over SNR, you can allocate a lot of power. The water level is set in such a way that the total area satisfies the total power constraint. When we have a larger power constraint, we can raise the water level, so bring it up. Or when the transfer power is less, we can reduce the water level, bring the water level down. What we've seen in this lecture is that you should be able to explain the goals of adaptive transmission, benefits and drawbacks, solve rate and power adaptation problems, and also implement statistical and deterministic water filling solutions.